last Monday we stopped more or less at this point when we were discussing about the calculation of the stress distribution when we have a glued a joint with glued in bars, rebars, like the one that you see here. So the idea was that if we consider this cross section here at the interface between the beam and the column, this cross section may be considered as having a similar behavior to a reinforced concrete section, where basically we have a cracking in the reinforced concrete section. So in other words, if you do a cross section here, we will find that if we have a hogging bending moment, which means a negative bending moment, you will have some compression at the interface between the column and the beam, in this shaded area. And then you will have detachment in the upper part. So basically you have no contact, so no tension on the white area of this beam cross section. So this kind of distribution, if you want this distribution of stresses here, is similar to the distribution of stresses that we have in a reinforced concrete beam at the cracked limit state. If you remember talking about reinforced concrete, we make a distinction between what we call stage 1, uncracked cross-section, stage 2, cracked cross-section, and stage 3, ultimate limit state. So this is looking at this connection between a timber beam and a timber column. In this discontinuity section, we have a distribution of stresses which are linear, basically in timber, because we said that timber is more or less an elastic material, so we can expect having lots of plasticity in compression here. And it's also linear in this part here, so basically we assume also for this type of cross-section that we have a conservation of the plane section. Like the same hypothesis that we used discussing about reinforced concrete section at in cracked phase. So in the end, we can use the same formulas that we derived for reinforced concrete in the cracked phase, also to solve the distribution of stresses at the interface between the beam and the column in this type of joint here. So we derived last time, if you remember, we started by writing the equilibrium between the tensile forces into the upper bar and the compression forces in the lower bar into the timber itself. Then we calculate this compression, tensile force and compression force in the timber and in the steel. Then we use the constitutive relationships, so linear relationships for both timber and steel, so we don't consider any plasticization here. Congruence, so basically a plane section remains plane after the deformation, so these are the same kind of relationship that you may recall finding in reinforced concrete, in the reinforced concrete course. And then of course when you replace epsilon s prime discontinuity equation with the congruence, and then this one in the other equation, at the end you get a second degree equation, the same that we were using in reinforced concrete design to find the position of the neutral axis. And from that we have only one solution which has physical sense, the one with the plus here rather than the minus. And then the Navier formula can be used to calculate the sigma. So the sigma into the wood, the maximum stress, compressive strain to the wood, is the bending moment m divided by the second moment of area of the homogenized cross section with respect to the neutral area times epsilon, so y, which is the distance of the neutral axis by the compressive fiber, and then for the steel we have this other equation here. So the second moment of area is calculated by using the transform section method, basically. So it's the second moment of area of this shaded rectangle plus the moment of the rebars multiplied by n, which is the modular ratio. Exactly the same formula that we found for reinforced concrete design. So these formulas allows us to calculate based on the external bending moment in the joint. So you have your portal frame, for example. You will start your design, so you have a portal frame. You analyze the portal frame with sub 2000 or by hand, whatever you want. Then you will find the bending moment in the connection there. And from the bending moment, you will use this formula here to calculate the stress distribution into the wood and the actual tensile compression force into the epoxy bars. Then you will have to design the epoxy bars for this tensile force obtained from this formula here. Now, the work example that we're working on is slightly more complex because in this case we are considering the case of an extended beam. So we have a beam which extends above the timber column, meaning that in this case, at the interface between the timber beam and the column, in this cross-section here, we will have a bending moment, which will be negative, and then we will have also an axial, a compressive axial force. So in the end, it's a problem of coupled bending and axial force. So in this case here, as you may recall from reinforced concrete design, we have to use different formulas to find out the neutral axis position, and then we will solve a third-degree equation to find exactly the position of the neutral axis. So basically in our cross-section we have a negative bending moment and asterisk, and we have a compressive force and asterisk. We can, first of all, if you remember, we can calculate the eccentricity of the axial force. So the eccentricity of the axial force will be the ratio between the bending moment and the axial force. If the eccentricity is less than is within what we call the kernel, which is the Italian, is the nocciolo centrale di inerzia. So if this E is less than 1/6 of the H, then of course we have the neutral axis is outside of the cross-section, so all the cross-section will be compressed. Instead, if the eccentricity is larger than 1/6 of the depth, then we have what we call large eccentricity, and then the neutral axis will cut the cross-section, and so we will have a part of the cross-section which will be compressed, and another part which will be in tension. So the timber will be reacting only in one part of the cross-section. Usually, when you design a portal frame with epoxy rods glued, usually you will have that bending moment will be much larger in proportion to the axial force. So usually this will be the case. So here it will be a case of large eccentricity and a case of partial resistant cross-section. So now the problem is to find out the position of the neutral axis. If you remember, this is a problem since we don't know at the start of the problem which part of the cross-section is compressed, which part is in tension. We need to find the position of the neutral axis of this quantity y. So to find the position of the neutral axis, we can write down the equilibrium of the bending moment around this line 1, 1. So the equilibrium of the bending moment around the position of the eccentric axial force. So, what are the actions that are present in our cross-section? Of course, we have the eccentric axial force, whose moment around 1, 1 will be 0. Then we have a compression force, which is the resultant of all the compressive stress in the timber, so C. So C multiplied by, if you want to make the equilibrium, the bending moment of this force C with respect to this line 1, 1 will be C times E, so E is the eccentricity, so E minus h divided by 2, so E minus h divided by 2 is this distance here, plus y divided by 3. So C is basically in at 1/3 of y, and then this 1/3 of y we need to sum E minus h divided by 2. So this is the bending moment of C with respect to 1, 1. Then we have the bending moment of C prime, which is the compression force acting into the bar, which is glued into the wood. So C prime, in this case we will have to do C prime times, again, E minus h divided by 2 plus D prime. And then we have the bending moment, the contribution of the bar, which is in tension on the opposite side. So since it is a tensile force, we need to multiply the tensile force T by the distance from 1, 1, which is basically D plus E minus h divided by 2. In this case, with the sign minus because it's in the other. This one is clockwise, while the two forces before were producing a moment which was anti-clockwise. So this is the equation, equilibrium. Then again, we replace C prime and T with this relationship. So C is 1/2 of the sigma in the wood times B, breadth of the bead, times Y. Then again, we consider the constitutive relationships and the same congruence equation as last time. So if we replace epsilon s prime and epsilon s in this constitutive relationship, and then this stresses here into this other equation, then this C prime and T into this other equation, in the end, we get this equation you can find here. We can simplify in this equation the epsilon WL in the wood. We can multiply by Y and divide it by EW, where EW is the modulo of elasticity of wood. And then you see, in the end, we get this relationship, which is clearly a third-degree relationship in the unknown Y, which is the distance of the neutral axis by the compressed fiber of the wood. Again, we get to this equation here. So here, yes, this is a third-degree equation, so A y cube plus B y squared plus C times y and plus B equal to 0. Third-degree equation. So we can solve this third-degree equation using, for example, the gold sig function of Excel, like we've done 2 years ago in the other course. And once we calculate the position of the neutral axis, then we can calculate the stress distribution. For the stress distribution, just a reminder that we cannot use the principle of superposition. So in this case, we cannot say sigma equal to, let's say, n divided by a plus n divided by j by y, because it's a nonlinear problem. So we cannot use the principle of superposition. So we have to use those relationships that we derived in the course of reinforced concrete design, studying exactly this case here. If you remember, if you go back to see your notes, sigma WL, so the maximum stress, compressive strength into the wood, is minus the axial force, compressive axial force, divided by Sx. So Sx is the first moment of area of the homogenized of the transformed section, basically, with respect to the neutral axis. So this axis is the axis number 3, times y, where y is the distance of the fiber from the neutral axis. Then sigma s prime, so the stress into the compressed rebar is similar to this one. In this case, we have to remember to multiply by the n. N is the modular ratio. N is basically the ratio we see between the modulo of elasticity of steel and the modulo of elasticity of wood. And in this case, the distance is y minus d prime. And the last one, the stress into the rods subjected to tension is n times n asterisk divided by Sx times d minus y. So Sx, as I said before, is the first moment of area of the transformed section with respect to the neutral axis. So we have first a contribution of the timber, which would be b times y divided by 2. Then we have a contribution of the homogenized and transformed section, the transformed steel here. So n times s prime, as prime times this distance. So this distance is y minus d prime, minus, because it's on the opposite side, n times as times d minus y. Now, the important point is the choice of the modular ratio. Of course, in reinforcement design, the modular ratio, if you remember, was very simple. It was very simple. It was the ratio between the module of elasticity of concrete, sorry, the module of elasticity of steel, and the module of elasticity of concrete. And the regulation said that in that case, you can use always the value of 50. This is the type of regulation. In this case, there is a doubt here, because if you look at the cross section, so when we're going to do this check, here we will have a contact between wood parallel to the grain and wood perpendicular to the grain. So on this side, so here we will have an opening of the joint, so we will have something like this because of the bending moment. So here we have contact, so here we will have a distribution of stresses, something like this. Then here we have a rebar, tension, and here we have another rebar, compression. Now, on this side, on the side of the beam, how should we calculate the modular ratio? So, on the side of the beam, n should be equal to what, in your opinion? On this part here. The modular ratio should be the ratio between what? Yes, so n equal to E divided by which E?
ES divided by
ES. So ES is the module of elasticity of the steel, of the rebar, divided by the module of elasticity of wood perpendicular to the grain on the beam side. However, on the column side, N will be given by what? ES divided by E W 0, because here you see the wood is pressed parallel to the grain. So there is a doubt about which kind of modular ratio to choose. So how to calculate the modular ratio will be ES divided by EW90 or ES divided by EW0. Just a reminder that EW90 is 1/30th of EW0. So if you want EW0 is 30 times, is between 20 to 30 times larger than the other value. So there is quite a significant difference between choosing these two different values. Now, if you want to make a conservative calculation, it is not clear here, the regulation doesn't say anything. As I mentioned yesterday, this part here is not dealt with by any regulation in the world. So you cannot find anything. So there has been done some research, I read some papers, read scientific papers, and in the end, the idea is that if you want to make a conservative assumption, conservative calculation, since we are not sure, it's better to refer to the module of elasticity of wood perpendicular to the grain. So in order, if we have to do a calculation of a joint like this, by using the module of elasticity of wood perpendicular to the grain, we will get a lower lever arm, and so we will get a more conservative calculations. So, in the end, the suggestion is to use this kind of modular ratio. So, N equal to ES divided by EW90 to solve the problem. So, now we go back to our design, the design we started yesterday. If you remember, we did a preliminary design yesterday, and we assessed that we will have to have at least one column with a depth of 1,180 millimeters. The breadth shall be the same as the breadth of the beam, 200 millimeters. So we can calculate the eccentricity as a ratio between the design moment and the axial force is 1.8 meters, as you can see, 1,833 millimeters. So we are in a case as predicted, we are in a case of large eccentricity. Now, if you remember, in our cross section, we had a situation like this. If we draw our cross section, the cross section of the column. The section of the column is something like this, with, as we said, 4 bars in tension and 4 bars in compression. Okay. Now, the formula that we derived in reinforced concrete design, the same formula that we wrote before, they have been derived considering not a situation like this, but a situation with a unique, with only one line of rebar. So basically it's a cross section like this. So those are the formula that we used in reinforced concrete design. Reinforced concrete design, we always had only one line of bars, not more lines. Okay? But in our case here we have 2 lines of bars. So how do we solve the problem? Either we rewrite again all the equations, which will become a bit more complex, because we need to take into account that we have 2 lines of bars. So we have a different contribution, or what we can do a simplification. We can just assume that those 4 rebars here are concentrated, like if there were only 1 bar, concentrated in their centroid. In other words, we can solve a problem like this. So we replace those 2 lines of bar with only 1 bar concentrated in the centroid of those 4 bars. Okay? Of course, this is an approximation, because this is not true, but the mistake that we have in this case is very little, considering that those 4 bars are not too far away from each other. So what we do, we move from this cross section to this cross section. On this cross section we go to solve and to find out, for example, the neutral axis, y. Okay? So we use the same equation as before. Once we have concentrated the 4 bars into only 1 point, we use the same equation as seen before to calculate the neutral axis, which was, I think, xx. To find y. And then when we go to calculate the stresses to the rebar, so we would have, for example, a stress distribution like this. When we calculate the stress distribution, of course, if we go to calculate the stress distribution only in the center of the rebars, you would get a value that would be slightly non-conservative. Because in the reality, you see that there is one bar a little bit more closer to the end of the cross-section. And this bar here would have a slightly higher stress. Okay? So, the suggestion, therefore, is that we do it this way. In order to find the neutral axis, and also the second moment of area, the first moment of area, and so on, we replace the 4 bars with only 1 bar in the center. But then later on, in order to find the maximum stress, we go to calculate this maximum stress not in the centroid, but in the actual position of the most, let's say, of the bar which is closer to the end of the cross-section, in order not to make a non-conservative calculation. It's clear? What? Sì. So we repeat in Italian. Per semplificare il calcolo della posizione dell'asse-neutro, per non dover scrivere tutte le equazioni, che si potrebbe anche fare, non sarebbe un dramma, però insomma comunque sarebbe una perdita di tempo, andiamo a concentrare tutte le barre nel baricentro delle stesse barre. A quel punto quindi andiamo a trasformare la nostra sezione reale in una sezione con sole 2 armature, con sole 2 file di barre, che è la sezione che abbiamo sempre considerato per quanto riguarda il segno. Quindi ci calcoliamo la posizione dell'asse-neutro con le formule viste prima, che a questo punto sono rigorose. A quel punto, quando vado a farmi la verifica delle tensioni, lì, se vado a calcolare le tensioni sul baricentro, trovo un valore inferiore rispetto a quello reale, perché la barra, nella realtà, la barra, vedete, ce n'è una che è un pochino spostata più verso la fine della sezione. Allora, per non fare un calcolo che sarebbe in sfavore di sicurezza, il suggerimento è fare l'approssimazione sul calcolo dell'asse-neutro, delle barre concentrate. Poi però quando vado a calcolarmi la sigma me la calcolo non a livello del baricentro delle barre, ma a livello della barra più vicina, della barra più sollecitata, di quella più vicina alla fine della sezione. È chiaro a tutti? Bene. Così procederemo quindi. So, going back to our formula, d prime, see, since we have 2 lines of bars, d prime in our case becomes this. So this quantity is called d prime. This is A2T, and this is A2. So d prime is A2T plus A2. Maybe yesterday, I need to go back, but maybe as a result of the preliminary design, maybe we decided to use not 4 bars, but actually 6 bars. Let's go to see, because I can see otherwise there is a mistake. I don't think so. So if we go back, we need to see what was the result of the preliminary design. So the first design was 2 bars, 20 mm diameter. The second design was 3 lines of rods to reduce the color gap. So at the beginning we started with 4, and then we said since with 4 we will get a color which will be too big, it's better to increase those 4 bars to 6. Okay? In order to reduce the breadth of our column. So what we have is slightly different. We need to replace this. In the reality, what we have is something like this. Okay? So before I did a round of drawing, so this is our actual case. So 6 bars and 6 bars. At least they are now designed as 6 bars in this position here. So D prime, this is D prime. So this is A2 and A2T. So D prime, as you can see, D prime is A2T plus A2, so 180 millimeter. D second, same thing, A2T plus A2, 180 millimeter. So the area of the rebar is basically 6 times the resisting area of one rebar, 1,470 square millimeter. And S prime, so this one is AS and this is S prime, same thing, 1,470 square millimeter. Now we calculate N. ES divided by EW90, 700. So as you can see, the modular ratio is not more like 6, 7, or 8 like for endoscopy. This time we're talking about 700 because it's a huge difference between the young modulus of steel and the young modulus of the wood perpendicular to the grain. This is the young modulus of glue lamp perpendicular to the grain, 300 megapascal. So now we can calculate the neutral axis position. We have to solve this third-degree equation, A, B, C, and D. So A is B divided by 6, 33.3 millimeter. B is this other quantity here. C is given by this other value here, and D by this other formula here. So we get the 4 coefficients, and then we can solve this third-degree equation using the goal-seek function of Excel. Do you know how to use the goal-seek function of Excel? Well, the students who attended the course of endoscopy, they should know, because I think we discussed how to do it. What about the other? Never heard about this function in Excel? Okay, this is a function I can show you. Quite simple. With this goal-seek function Excel, you in maybe one fraction of a second, you can solve a third-degree equation. So okay, so this is an Excel spreadsheet, as you can see. So coefficient A A, B, C, and D. Inside here, you can see there are the formula. For example, well, of course, the formula you cannot see because they are inside the software. For example, A is basically B divided by 6, and then all the others, so here we have different values. So A, B, C, and D, so the coefficient, then Y. So Y is our unknown. So while A, B, C, and D are formulas, as you can see inside here, there are different formulas. Y is a number. So what you can do, you can set up an initial value of Y, 400, for example. We don't know how much will be. Of course, if you're expecting something between, I don't know, in our case, it will be between 0 and 1000, you don't put 1 million inside that. You put 100, something which is that may be reasonable, because otherwise the program may not convert to the right solution you can imagine. So you put 100, and then you go on the function here. Let's see if we find it. It should be between data. We have to go to data. Data. And then from data here you find at a certain point there is what if analysis. So you click on what if analysis and you choose goal seek. So goal seek, set, no, what is this? Yeah, set cell. So set cell, this cell here. So the cell of our unknown is the one that we set. So set cell E41, which is our unknown, to value. So, sorry, I made a mistake. Set this value here. You see function, and I miss one important point. So we said that those are the coefficient of the third degree equation. So let's write it here. So this is the third degree equation that we need to solve. So first, we write down the value of the four coefficients, A, B, C, and D. Then we write down Y, which is a number, our unknown, and then we write down F function, which is written as this function here, which is A y cubed plus B y squared plus C y plus D. So inside here, if you go here in function, this is basically so this one is basically A times y cubed plus B times y squared plus C times y plus D. Okay, so this is the value of this function basically. Now, what we have to do with Excel, we have to say that Excel has to find y such that function of y is equal to 0. So in the end, we say to Excel, let's go back where we were before. So, what we said, data, what if analysis, goal seek, set cell, so set cell, this cell here, so set the cell of the function to value 0 by changing cell y. So basically we are saying to the software, find out the value of y such that this function here is set to 0. Okay? Now, you say okay, And you see in 1 second you get the solution. So y shall be equal to 1049 millimeter. Okay? This is the way that we can use Excel to solve that degree equation. Is that okay? Is that clear what we do? Okay. Okay. The degree equation is solved, and we get this first solution. Y equals 734.8 millimeter. Then we can calculate the first moment of area, and then the maximum stress into the wood, which is 0.67 megapascal. So 0.67 megapascal is less than design compression strength perpendicular to the grain, which would be 0.9 times 2.5 divided by 1.25, so 1.8 megapascal. Then we need to calculate the stress of the rod loaded in tension, so the stress above here. So sigma s is N times ND divided by Sx times, in this case we said that we want to get the actual value that I have not in the centroid, but at the actual position of the cell of the rod. So the rod is here at a distance of d minus y plus a2. So basically at the actual distance here. So d is up to the centroid, so this will be d. D minus y is this distance here plus a2, this distance here, in order to get the actual value in tension that I have on the position of the most of the rods which are further away from, closer if you want, to the end of the cross section. And you can see that here we get to 296.1 megapascal. If now we calculate the design value of the yield stress into the rod, we get 285.7, because this is 300 divided by 1.05, so 285.7. So this verification is not satisfied. So the tensile stress, which one, stress in the most tension rod is greater than the design strength. So this the design is not satisfied. In compression is even worse. If you see in compression, we get 416.9 megapascal, which is by far larger than 285.7. So this first design is not okay. It's not okay because the wood would be okay, but we would get some failure into the rods, particularly into the compression rods. So, in order to make the design and ultimately maintain the rods satisfied, what we have to do, we need, unfortunately, to increase again the depth of the column. So we need to increase the depth of the column, and then we need to realize that we have forgotten to do another important thing. We have forgotten to consider the group effect of the rods. If you remember, when we have more rods working together at a certain distance, their load carrying capacity is not simply the sum of the load carrying capacity, or the load carrying capacity of one multiplied by the number of rods, because we have an interaction. So we have to consider the effective number of rods. Same thing that we know we are doing for the balls or for the doubles when they are aligned along the grain. So we need to use this formula here. So basically, if you have, for example, 6 rods, so yeah, like now, okay, you have 6 rods, the load carrying capacity of those 6 rods is It's not 6 times the load carrying capacity of a single rod, but is 5 times the load carrying capacity of a single rod. So these 6 rods, when they work together, it's like having one less. Because you see the formula, effective number of rods is number of rods to the power of 0.9. So 5.02. Meaning that when it comes to calculating area of the rod's in tension, we need to multiply the resisting area of one single rod by the effective number of rods, by 5. So the area becomes 1,229 square millimeter. So the column depth now is increased to 1,760. So it's increased quite significantly to take into account that we have to make this alternative state design satisfied. So D becomes 1,580 millimeter. Then we have to rewrite again the third degree equation. We have to recalculate the 4 coefficients, so A, B, C, and D. And then we need to solve again the third degree equation. If we solve the third degree equation exactly as we did before, now we find out the position of the neutral axis given by 1,049.1 millimeter. We calculate the first moment of area of the transformed section with respect to the neutral axis. And then we can recalculate the stress in the timber. The stress in the timber before was satisfied. Also in this case again was satisfied, as you can see. 0.43 is less than 1.8. And then we need to see what's happened, what's going in the rods. In the rods, if we recalculate again the tensile stress in the tensile rods, we get this time 182.7 megapascal, which is less than 285. For the compression rods, we get 280.7 megapascal, which is less than 285. So which is sized by having increased quite significantly actually the depth of the Bluetooth column, we can get that the ultimate limit state this time finally is satisfied. Of course, we can see that in tension, there is quite a significant difference between the, let's call it the strength demand, 182 megapascal, and the strength capacity, 285. So one may think that perhaps here we have been using too many rods. So we could have used less than 6, for example 4, because you see that there is quite significant difference between those two functions. So the design doesn't seem to be done well. So if we reduce the number of tension rods to 4 instead of 6, of course we need to change all the different quantities. We need to recalculate the effective number of rods. And so we calculate the area of the rods in tension. We recalculate again all the coefficients of the third degree equation. We solve again the third degree equation, we find the solution here. Y is 962.2 millimeter. So this is the depth of the compressed area in the wood. We recalculate again the first moment of area, the transformed section, and the stresses in the wood. Stress in the wood is almost the same as before. The tensile stress in the tension rod, as you can see, is slightly higher than before 180, now this time is 128, it is smaller than the actual capacity, 285.7. And also the other, the strength demand on the compressed rods is less than the strength demand, the strength capacity. So we could say that yes, it was possible to have a better design by reducing the number of compressed rods, the number of tensile rods from 6 to 4. Another problem we have to consider is that the compressed rods, so we have 6 compressed rods, but due to the compressive rods, those rods may have problem buckling. So now, so far, we just assume that those rods can carry their yield capacity without any problem. But in the end, since they are subjected to compression rods, to compression loads, they could buckle, they could have problem of flexural buckling, the same as the case of the screws, of the compressed screws. So, we need to avoid that we have on this rod this kind of buckling effect that you can see here. So in order to check the problem of buckling, we can use the formulas that we have already used for screws in compression. Formula taken from the Euro 3. So basically, like having a beam which is subject to a compression load, but is not free to buckle because it's surrounded by linear, the wood, which acts as a bed of springs, basically, a number of springs. Now the formula are the same that we saw a while ago. So this one is the design axial resistance of the rod, of the compressed rod, which will be this reduction coefficient times the characteristic plastic failure load of the rod divided by the safety coefficient. The reduction coefficient, as you can see, depends upon the relative slenderness ratio. K is given, also this coefficient K is related to the relative slenderness ratio. The relative slenderness ratio is the square root of the ratio between the plastic capacity of the compressed rod and this critical load. So the plastic capacity is basically the section modulus of a circle times the yield stress of the steel, and this other critical load is the square root of the product between this coefficient, which is related to the stiffness of the springs, the wood, and the flexural stiffness of the rod cross section. So CH is related to the diameter of the rod and to the characteristic density of the wood, which is going to affect in some way the stiffness of those horizontal springs. Alpha is the angle of inclination, of the angle of the rod with respect to the grain. So ESIS can be calculated as ES to 210,000 times pi d squared divided by 64 is basically the second moment of area of the section of the rod with respect to the diameter. So if we replace these symbols here with the numerical value here in our case, so we can calculate the equivalent diameter of the rod, 17.66 mm for the resisting area of the rod, and then plastic capacity, flexural stiffness of the rod, and then we get this value here of CH equal to 85.4. Then this critical load is in the end is equal to 292,707 Newton. The relative stiffness is 0.5 and the reduction coefficient K is 0.7. So this other reduction coefficient Kc becomes, in our case, 0.84. So in the end, the design buckling resistance for our compressed rods is, instead of 73,500, is 61,914. So we have basically a 16% reduction of the load carrying capacity due to buckling, flexural buckling, which means that our limit value for one single rod will be basically 280.6. Well, if you want, this is the capacity, 61,114, and this is the demand. The demand is 68,747. So the demand is larger than the capacity. So we saw that due to buckling, actually, the design is not satisfied. Because we have that we may have a failure due to buckling of the rod compression. So as you can see, the design is not so simple. We have to make an assumption, you have to check, then to correct the value and so on. So you have to continue changing until everything, all the verification is satisfied. So what we have to do, either we increase again the breadth of the column, or we increase the number of rows. Since our column depth is quite big, we can think about increasing the number of rows from 6 to 8. This means that we need again to change V prime. The V prime, as you remember, is the distance between the centroid of the bar and the side of the cross section. We need to recalculate AS prime. We need again to recalculate the coefficient of the third degree equation. And then we need to solve this third degree equation using again the M&MoCS function. Final result is the distance of the neutral axis from the compressed fiber is 881.5 millimeter. We calculate the first moment of area of the transformed section with respect to the neutral axis, and then we can calculate again the stress into the wood, which is even less, this time 0.38, the stress into the tensile rods, which is 241 less than 285, and the stress into the compressed rods, which is 242.3 less than, you see, the actual strength, buckling strength, which is 252. So by increasing the number of compressed rods from 6 to 8, finally we can get to this design inequality satisfied. So our design is finally okay. So basically, based on these results, what do you think? What would be the sequence of failure of the joint? So suppose that your joint increase the loads. So keep increasing the loads, so increase the bending moment, and at a certain point you will have what sequence of failure? So what is going to fail first? So if this is the verification, where do you expect to have the first failure in your elements? So then we are checking 3 different components. We are checking the wood, we are checking the steel, the bars of compression, we are checking the bar tension. Suppose that the loss is going to increase because you have an exceptional rod. What would you expect to be the failure mechanism?
The column.
Yes? Where?
Because the buckling giving attention to
Okay, but just forgetting about this problem of secondary stresses. If you look only here, these 3 checks. So if I ask you, would be the wood, would be the steel of the compressed rods, or would be the steel of the tensile rods? What would be the answer? The steel of the compressed rods, exactly. But as you said before, this would be a failure for buckling. So this is the right comment. If the bar is going to buckle, it's going to also to break the wood. Where is going to break? This wood here, parallel to the grain, or this wood here perpendicular to the grain? It's probably going to buckle here. So this buckling of the steel will occur simultaneously with the failure for splitting of wood, splitting perpendicular to the grain. After that, probably is going to break, that's it. But if we could have a redistribution force. After that, what would you expect to be the next one? Based on the number you can see here.
The first mechanism is about sigma.
The first is this. The second, so this is it going to occur? You're going to have a failure for yielding of the tensile rods, or a failure for compression perpendicular to the grain here on the beam. Perpendicular to the grain. Well, we need, as usual, we need to do the ratio between the strain demand and the strain capacity. So here, strain demand 0.38, strain capacity 1.8. The ratio would be 1.6. If we do a ratio between the strain demand in the tensile rods 141 and the strain capacity 185, this would be 5.6. So this is much closer to failure than this. So if we had, this is not the case, but if we had the possibility to redistribute the stresses, after the failure for buckling of the compressed rod, we would get the failure for stretching, so the failure in tension for EAD of the tensile rod, and only at the end, the failure for compression perpendicular to the grain. Okay? Okay. Now, another important point, if this connection was considered as dissipative in seismic region, we would have to ensure that, if you remember, a joint to be dissipative in seismic region must be characterized by yielding of steel. So, would a joint like this be okay as a dissipative joint in the seismic region? Is it characterized by a yielding of steel, the failure in this case? No. No, because the failure is actually for buckling. So this wouldn't be okay. This joint cannot be considered as dissipative. Particularly, if you remember, first of all, this should be the dissipative, so the yielding of the rods in tension should be the dissipative failure mechanism, and that should be the first to occur. With respect to tensile failure in the wood and bond failure at the timber, at the glue timber interface. So in our case, we don't need to satisfy this condition for two reasons. First, because actually in our case, this is not the right failure mechanism, because the first failure mechanism to occur is compression, not the tension. And second, because this is not a dissipative joint in seismic region. Now, in any case, if possible, it's better to ensure that the yielding of the rods, also the vacuum of the rod in compression, will occur before then these other two failure mechanisms that are very brittle. So the two very brittle failure mechanisms are failure in tension of the wood, this one, and failure of the bond. Even though in this case, it is not necessary, for this case that we are now analyzing, to do this kind of check. If you want, as a matter of exercise, we go to apply this criterion here to our case. So basically what we say is this. In our case, we're going to design the length, for example, of the rods and the connection in such a way that the failure of the timber and the failure of the glue cannot occur before either plasticization, so heating of the rod, or buckling of the rod, by using this overstrength coefficient 1.5. I'm just repeating, in our case this is not necessary, this criterion, but as a matter of exercise, we are going to see what kind of results we can get if we want to satisfy this criterion also in our case, okay? So, the maximum stress into the rods, the tensile rod is 241.4 megapascal, which is less than 285.7 megapascal in tension. So, we need to basically find out the value in tension associated with this level, with this stress level, so 241.4 times 1.5, and then we need to make sure that these other two failure mechanisms are designed for the value that we obtain here. So 1.5 times for the tensile rods, so 1.5 times the sigma, we need to multiply by the effective number of rods divided by the actual number of rods times the resisting area, we get 77,182 Newton in terms of this overstrength force, let's call it overstrong force in the tensile rods. So basically we have taken the actual force, which is this value here, we will multiply by 1.5 to make sure that the actual plasticization will will occur always before the other two tension mechanisms, the other two failure mechanisms. So the other two failure mechanisms that we need to check first is failure of foot parallel to the grain at the end of the rod. So ultimately the state of tensile stress parallel to the grain at the end of the most stressed tension rod. So this is the most stressed tension rod. And we need to calculate the stress into the timber at the end of the rods. So we need to take basically a kind of tributary area of the wood surrounding the most loaded rods, AEF, which is half of the breadth of the cross section times A to C plus A2 divided by 2. So it's 13,000 square millimeters. Then we calculate on this cross section of wood, we calculate the tensile stress parallel to the grain, which would be sigma T0D is 77,182 divided by 13,000. It's 5.94 megapascal. So 5.94 megapascal is less than the design strength of wood parallel to the grain. The design strength of wood parallel to the grain would be 16.1 megapascal. So basically what we have checked now is that we won't have any failure at this end of the rods in the column. However, we may have a similar kind of failure also in the beam, at the end of the rod in the beam. In the beam, which kind of strength we should assume for the wood in the beam at the end of the rod? So here, we have considered the strength of wood parallel to the grain. Here, perpendicular to the grain. Now, strength of wood perpendicular to the grain is 0.5 megapascal. This is the characteristic tensile strength. Then you multiply by 0.9 divided by 1.25, you get 0.4. The demand is 5.94. How can we make this design satisfy? So strength demand 5.94, let's say 6. The strength capacity is 0.4. Is there any way we can make the design satisfied? There is two large difference. So no way we can make this design satisfied. So the only way we can do here to solve the problem is basically to go and to bring the rods until the end of the cross section. So to glue the rods all the way through the depth of the beam. This way, we don't have this problem of splitting of this problem is possible splitting of wood perpendicular to the grain until the end of the rods. Okay? Of course, doing this is quite demanding in our case because our beam is 1.6 meters deep, if you remember. So it means that you have to have a rod which is long 1.6 plus another 1 meter, you have 2.6 meters. As you can imagine, to glue a rod which is 2.6 meters into holes which are just 2 or 3 millimeters wider and which are long 3 meters, it's very difficult, very complex. That's why I said that this is a more kind of theoretical exercise because you can design something like this, but then to construct this joint would be a kind of help for who would have to do it. Because, okay? Then we need to calculate the minimum anchorage length of the most compressed rods. So what would be the anchorage length in order to ensure that we don't have debonding? So we don't have a detachment of the rods from the wood. Again, we calculate the demand and we compare the demand with the capacity of the rods for failure of bond. So for failure of bond, we calculate pi times the equivalent, which is basically the perimeter of the hole, times LAD, which is the bonding length, times FVD, which is the design strength, the bond design strength. So FVD is K mod against FVK divided by gamma M. And so from this equation, we invert this equation to find the minimum bonding length. So LAD is here the only unknown. So LAD shall be greater than or equal to 1.5 FAX per RD divided by this quantity. We have to remember that by regulation we have a minimum anchorage length, which shall be, you see, the minimum anchorage length is the max between 0.5 times D is the diameter of the rod, so 20 millimeter squared, so 200, and 10 times D is 200, so 200 millimeters. So the minimum bond length is 200 millimeter. Another problem is that in this equation we have FVK. FVK is the characteristic bond resistance of the glue. But the characteristic bond resistance of the glue depends on the L, which is unknown. So we cannot invert directly this design inequality. So we need to start by making a conservative value of FVK. So if we go to C, FVK depends on the glue length. So if the glue length is less than 250, it is 4 megapascal. If the glue length is between 250 and 500 millimeters, is given by this relationship, and if the anchorage length is between 500 and 1000, it is given by this relationship here. So we can start by assuming that the bond length is 1000 millimeters. If the bond length is 1000 millimeters, FVK is given by this relationship here, so it's 2 megapascal. The equivalent diameter of the bond is the minimum between the diameter of the hole and 1.05 diameter of the rod. So it's basically 1.05D, so 21 millimeters. And so if we replace inside all this value, so the equivalent FVK, which is 2 megapascal, we get the minimum anchorage length in the beam. Which is basically 1000 millimeters. So for the minimum anchorage length, bond length of the bar in the column, we can assume 1000 millimeter. Then we need to calculate the anchorage length also in the beam, which is different from the other one. Why is different? It's different because in the column the rods are bonded parallel to the grain. In the beam the rods are bonded perpendicular to the grain. So also the strength is different, the bond strength is different. The bond strength, as you can see here, depends on the angle alpha between the rods and the grain. So in the column alpha is equal to 0. So you get that FB alpha K is equal to FBK. But instead, in the beam, FB 90K is 1.5 FBK. So we have a larger strength. Having larger strength, we can expect also a lower bond length. So in this case, we can start by assuming a bond length in the beam of 250 millimeter. So FB 90K becomes 1.5 times 4, so 6 megapascal. LAD would become, in this case, as you can see, 338.9 millimeter, so 400 millimeter. But with 400 millimeter, the FBK is different. So we have to do some iteration because with 250, FBK would be 4. With 400, FBK, as you can see, is 5.25 minus 0.005 LAD. So, FB 90K becomes 4.88 megapascal, which is less than 6 megapascal. So we have to assume an LAD of at least 500 millimeter. For 500 millimeter, you get an FB 90K of 4.125 megapascal. And then finally, we get to convergence. So we get the final result is 500 millimeter. So in the end, as you can see, this is our situation. We have 2 bars in tension, and 2 by 2, so 4 bar in tension, which are 1000 millimeter long in the column, and the whole depth of the beam, so 1600 millimeter in the beam. And then we have 8 bars glued in the compressed zone, which are 1000 millimeter long in the column and 500 millimeter long in the beam. Then what we are still to do, as you can see, lots of verification, what we are still to do is to check the compression perpendicular to the grain in the beam at this level, so at the tip of the compressed rod. So what may happen is that we may have a concentration of compressive stresses at the tips of this compressed rod. Those compressive stresses may produce plasticization within the beam because we are acting perpendicular to the grain, so they may be very low. So what we have to do in this case, we have to consider a distribution at 45 degrees of the stresses at the beam-column interface. If you remember before, we found out with this formula from the reinforced concrete theory that we have a distribution of compressive stresses perpendicular to the grain of the beam. Those stresses can distribute 45 degrees within the beam, and then we can calculate the value that we can get on the tips of the rods. So first of all, this effective length when we are going to do our verification of compression perpendicular to the grain will be, since this distance here is, well, it's 100, so 300 will be 500, because 500 is the length of the bond length of the rod into the beam. Since we have considered an angle of 45 degrees, it will be 500. 500 times plus 3 times 100, which is the spacing between the rods, plus another 500, so 1300 millimeter. So at this level, the stresses in the wood perpendicular to the grain will be given by the total force transferred by the rods, so MC times NL times sigma S times A resistance, which is the total force transferred by the rods, divided by the RF, so divided by LEF and divided by D, plus the value of the stresses at the interface between the beam and the column that we found before using the reinforced concrete formula. So sigma S is 197 megapascal, sigma W is the mean value of the compression stress in the beam at the interface with the column, so 0.38 divided by 2. In the end, this is the resistance, 1.8 megapascal. So if you replace in this formula the numbers, we get to see 1.68 megapascal, which is not so much less than the design 1.8. So 1.68 is very close to 1.8. So remember, when you do this kind of joint design, for sure you need to check at the beginning the stresses here. But we need also to check the stresses at the tip of the rod, because then you may have, like in this case, you have a kind of significant concentration of stresses. It's almost the value of the design. Okay? So, of course, when doing this verification, strictly speaking, we should do also the verification here. Do we need to do the verification here, in your opinion? Why? The resistance of the wood will be much larger here, because here we are talking about parallel to the grain, so we will have a much larger resistance. Here we are perpendicular to the grain. This is why, ideally, it would be much better in a joint like this to cut out this part of the beam and replace with a material which is isotropic, like for example steel. Because as you can see, most of the problem you get here, in this region here, not in the other region. Okay, in fact, if you remember, I showed you a picture where there was one joint without this piece, with a piece of steel there, with the rods, threaded rods with some bolts connected to this half of steel. Much better way, because they get rid of all this problem perpendicular to the grain. Okay. The last check that we should do to complete the design of the joint is checking of the rods for combined axial force and shear. Because if you remember, we said in this joint we have coupled axial force and bending moment, which are trying to open in the joint, which are basically stressing the steel, the rods, axially with an axial force. But then we have also to transfer a shear. As an equal shear. So, in this case, we need to use this interaction criteria, this quadratic interaction criteria, where we have to calculate basically the demand, the axial demand, in terms of the axial force demand and the lateral force demand, and we have to do the ratio between those demands and the actual capacity, the axial capacity and the shear capacity of the rod. Then we square both ratio with sum, and the sum shall be less than or equal to 1. In our case, the most stressed rod is the first on the right hand side. So this is the most stressed rod. So this one is where we have the maximum axial force. So we are going to check this rod for interaction between axial force and shear. For this rod, the axial, the demand, FAX SD is mostly 60 kilonewton, so 59,000 newton. The design battery resistance is 61,914. So as you can see, they are quite close to each other. So the strength demand is very close to the strength capacity. So we may have some problem because then we add another stress component, which is the shear. So we may have some problems with interaction. Even though here we are using a kind of quadratic interaction. The quadratic interaction is quite I would say tolerant for the material, because in a quadratic interaction you have block like this. So this is, for example, let's say that we put here AX. This one would be FAX RD, and this is FLA RD. So this is a quadratic interaction. So at the moment, you see that we are very close to each other. So FAX ST, the demand, 60,000, is very close to this one. So we are, in terms of demand, we are in a situation like this. So this is FAX RD, and this is FAX ST. So it depends now what will be this ratio here. Because you see, we are very close to each other, but fortunately we have a quadratic criterion, which is quite tolerant. Compare, for example, to a linear interaction criteria. In a linear interaction criteria, you would have very little possibility to take up any shear. But in our case, since we have this interaction criteria, there is some possibility to, despite the fact that the two values are quite close, to get also some strength, some additional strength for shear. So in our case, we need first to calculate the shear demand. The shear demand will be the total shear divided by the number of rods. Now the rods are stressed in shear, so they basically are like if they were the double type fasteners. So they are subjected to shear, so the strength demand will be the total shear divided by the number of rods. Number of rods, we have 8 in compression, 4 in tension, all of them are resisting to shear, so we do total shear divided by total number of rods. Correct. So 1.8 kilonewtons. And then we need to calculate the shear capacity of one single rod. Shear capacity is calculated using the Johansen formula for the bolts, assuming effective diameter equal to 90% of the nominal rod diameter. So 90% of 20 becomes 18 millimeter. The lateral capacity has to be calculated taking into account that those rods are aligned. In this case they are aligned perpendicular to the grain. In this case here they are aligned parallel to the grain. So since they are aligned parallel to the grain, we need to use this formula for the bolts to calculate the effective number of rods. So in this region here we have 4 rods aligned. So this is one group, then there is another group. So here we can consider 4 rods aligned, so 4 to the power of 0.9. If we replace inside the value 31 with 100, we get 2.82. And then we need to see the embedding strength. For rods glued in perpendicular to the grain, the characteristic embedding strength calculated with the formula for the bolts can be increased by 25%. And for rods glued in parallel to the grain, the characteristic embedding strength is assumed equal to 10% of the embedding strength perpendicular to the grain. So now we need to use the normal formula we already seen last time, if you remember, for the other example. So we need to replace inside here the formula for basically the embedding strength, the yielding value of the rods, and then the geometrical properties, the MP. Okay, actually I wanted to finish today, but since it's a little bit late, how many pages we still need to do this? Rather need to run and do this one. Okay. Do you think you can resist for another 10 minutes, or better that we finish here, we say goodbye and we finish tomorrow? It's a fire, you know, we are a bit on the limit. Yeah? Well, better tomorrow. Okay. So here tomorrow we just have this 10, 15 minutes more relaxing, and then we move to a new topic. So I don't know if you noticed, but before I send you a new presentation, this one. And this is very important because then after that, finally you can start. I think I already started with some design, but this one will be in some way helpful for the design that you have to do it for your single story. The idea is that this year we should finish this, hopefully, the single story design. Fortunately, it was not mine, so we should finish our single story design hopefully before this summer. So ideally before Christmas, but of course before the exam would be so not to bring like the other year, to bring it later, maybe 1 year after the exam. So the idea is that if now you are followed by Dr. Shomenta, you should try to work as much as you can until the end of the year in order to submit the project before the exam.